Hi friends, the Doppler effect. It is related to sound and you may have heard about it. But many students find it difficult to understand what it physically means, how to solve problems using equation that looks rather complex and to apply to real-time problems. Today what we'll try to do is to unravel some of those mysteries. For example, if you're asked to use this formula where there is V naught and Vs plus minus minus plus F and F dot, you'd find it rather difficult. But we will make it very easy and simple, and you will love what we have for you. Before we get into a sound wave, which is a longitudinal wave, and I'll come to the difference between longitudinal wave and transverse wave. But let's consider what a wave is. What are the parameters involved in a wave? As you can see, this is a wave, a sinusoidal wave. You can see it's moving from one direction to the other, right? I can increase the speed of the wave and it makes very slow, and this is very fast. Now, important thing to understand is what is the wavelength. You see the highs, these are the crests. The lows, these are the troughs. The distance between two crests or two troughs is basically the wavelength lambda. Then what is the amplitude? Amplitude is the from the mean, the center, the highest point, that's the amplitude. And again from the center to the lowest point, that's also amplitude. Then comes the frequency. The number of waves you encounter per second, the frequency. If you decrease the frequency, less number of waves per second. If you increase the frequency, more number of waves per second. Because the speed did not change, the wavelength changed and the frequency changed. So therefore, speed, wavelength, frequency, these are all connected, right? And how are they connected? V is equal to lambda f. This is something you should always remember. Also, frequency, number of waves per second, is also related to time period. Inverse of frequency is time periods. For example, time period, the dimension is seconds, frequency is hertz. So one inverse of second, inverse of time as a dimension is frequency. So 1 hertz is 1 by second. So now that you understand the basics of a wave, we look at what is a longitudinal wave. Now in a transverse wave, the molecules are moving perpendicular to the direction of the propagation of the waves. But in the longitudinal waves, for example, sound wave, the air molecules, when you produce sound, you compress or rarefy the air molecules, and those air molecules move along the direction of the propagation of the sound. So they oscillate along the direction of the propagation of the sound. They do not move, they oscillate. Now here you see this is a longitudinal wave, and if you decrease the frequency, you change the frequency and you decrease the speed, very slow, right? Increase the speed. So you can play with some of these parameters, but overall gives you the idea of what is a longitudinal wave. And we understand now how a transverse wave and a longitudinal wave essentially differ. Now we look at this compression, rarefaction, these two ideas. So as I was saying before, there is a source which is generating a sound. For example, you are speaking, right? You are generating a sound. And there's a listener, there's an observer or listener who is listening to the sound. Now, when you speak, you compress the air molecules that's between you and the observer, or you rarefy the air molecules. Compression and rarefication both are possible. Now, if you change the source frequency here, let's see what happens. That means more number of, higher frequency means more number of waves per second, right? So if you make it, you see more number of waves per second. See here. And now if you change this to very low frequency, less number of waves per second. Okay. So we understand rarefication, compression, and wavefront. Wavefront is a circle connecting all the points in the same compression. So these are the wavefronts, right? This is a wavefront. This is a wavefront, right? So now comes the reason why we are talking about Doppler effect. So suppose there is a source and an observer. Let's say you have two observers here, and the source is moving towards one and moving away from the other. So you have a situation where the source can be moving and the observer is still, or you may have a situation where the observer is moving but the source is still, and you can have a combination also, both the source and observer are moving. So what is the fundamental difference? So you have to look at some analogy. First situation is source is moving. Let's say the other case. Let's look at the other case. Observer is moving towards the source. So in a situation where observer is moving towards the source, whether it's moving towards the source or away from the source, the fundamental thing is the sound is being produced by the source. Therefore, the wavelength of that sound is same, constant. Nothing changes. That wavelength of that sound is constant. The velocity of the sound is known, the wavelength is known, the frequency is known. So what's going to change is only what the observer hears, right? Because the observer is moving towards or away from the source, therefore the analogy is like this. If you have cars, and let's say car is like the source of the sound, and the source is producing these waves which is represented by the cars. That when you are the observer, you are just standing there, and let's say the distance between the cars is the wavelength, then uh, that uh, that wavelength is the same. But if you are moving towards the car, towards the direction of the source, right? So in other words, the cars are going from left to right. The source has emitted the sound. It's going from left to right. And the observer is moving towards the source. That is going from right to left. This third problem, right to left. Then you are chasing the cars. So what will see, the cars are approaching you faster. You encounter more cars per second. If you are moving away from the cars, then the cars are chasing you. So you will see less cars per second. Now, if you try to look at it mathematically, let's say the case where the speed of the cars are 60 km per hour and the distance between each car is 100 meters. Then the time taken, it will be 6 seconds. That is if you are standing still there, then you are seeing a car every 6 seconds. Now, if you are moving towards the car, or towards the source rather, from right, you are going from right to left, third situation. Then what happens? Then your time that will see a car is going to go down to 4.5 seconds. So you are seeing that more cars you are seeing, right? This looks like going faster. And the second problem, where you are moving away from the source, there it's going to take longer, 9 seconds. Every car you see after every 9 seconds. So as you can see that the velocity, relative velocity, is going to matter. What changed here? 60 km per hour, and then if you are moving at a speed of 20 km per hour on the other direction. So second case 3 is 60 plus 20, 80 km per hour you are moving. That's a relative velocity. Okay. Then the time taken to see a car is getting shortened. Similarly, if you are moving at 20 km per hour away from the direction of the cars, then the time taken to see a car will get longer. So therefore, now if you try to understand and unravel that equation, what you are getting, let's do that. Now it will be easier to understand where we are. Okay, so here's the thing. This equation we already know, V is equal to lambda f. The observer moves towards source at speed VO, towards source. That means the second problem that we are, third problem that we are looking at. So when it is towards source, then you add up the velocity. So the relative velocity is V plus V naught. You see why you add up? Because you are chasing the cars. So the velocity is relative velocity is going to add up. You are going to see more cars per second, or the time taken to see a car will be less. So it's going to add up. So if the velocity adds up, and the wavelength is the same, so what is frequency? Frequency is 1 by time, right? So velocity divided by velocity is meters per second, lambda is in meters. So 1 by so if you cancel them, it will be 1 by second dimensionally. Now that's your frequency. That's what the observer hears. So question is, what's the relative velocity? When you are going towards the source, you are chasing the cars. You are chasing the cars means you are going to see the cars coming faster towards you. So you are going to have V plus V naught, which will lead to V plus V naught by lambda is a frequency that the observer hears, and lambda is V by F, velocity of sound in air, divided by frequency. And so essentially you will get F dash is equal to F times V plus V naught divided by V. Other scenario where the observer is moving away from the source. Same scenario where we saw for the cars, right? If we go back a little bit to recall, observer moving away from the source. In that case, it will be V minus V naught, because now cars are chasing you, and you are going to see less number of cars per second, or the time that will take to see a car will be higher. So the frequency, number of cars per second, right, is going to be less, and therefore it's going to be V minus V naught in that case. So now that part is clear, that okay, observer moving towards the source. What about the source moving towards the observer? So let's first try to understand the analogy for that. In this case, where observer was moving towards the source, the wavelength of the sound was fixed, right? But here what you have, let's say that I have a conveyor belt, and I have a machine dropping balls, let's say at a fixed interval, right? Now you see I have decreased the rate, and now it goes like this, right? Now here, if I make the machine move, machine which is dropping the balls, if I move, and machine is basically the source here. Now if the source is moving in the direction of the conveyor belt, that means towards the observer. So if I make this come here, then let's see what happens. So wait a little time and have an eye of this distance between the two balls. So this is one ball, and this is the another ball. So you see the distance has decreased, right? Distance has decreased. Distance decrease means that so the wavelength here itself, we are playing with the wavelength. Why you are playing with the wavelength? Because the source which is emitting the sound is now moving, and therefore you are playing with the wavelength. So how do I understand that? Okay, so this is one thing where the machine which was dropping the balls is now moving in the direction of the conveyor belt. The direction in which the conveyor belt is moving, it's moving in the same direction. So source is moving towards the observer. But if the source is moving away from the observer, the source is moving, let's put it somewhere here. Then you see what happens. So these were my original. These were after I moved the source towards the observer. And now let's see what happens. Now you see it's much bigger than even the original, right? Bigger than even the original. So what is really happening? Really what's happening is, if my source is moving towards the observer, then for the observer it's going to see more compressions. Let's look at something here. Look at this. Source is moving towards the observer. Observer seeing more waves, more compression. If the source is moving away from this is less compression. So wherever you place the observer, depending on which direction the source is moving, you're going to have higher or lower frequency. Now, how do you mathematically understand it, or physically and mathematically understand it? So let's look at the solution. So here what happens is that as I showed you for the conveyor belt, right? The compression 1 travels a distance Vt. Say, let's say for a time t, compression 1, once the sound waves are released, it travels a distance Vt. For the next compression, for the next wave to come, the source is also moving. So source moves with a velocity Vs for a time period t, same time period. The source has moved Vst. So the new wavelength becomes position of compression 1 minus position of compression 2. So Vt minus Vst. So, or V minus Vst. So T is basically 1 by F, and so lambda dash is V minus Vs by F. Now V minus Vs is which one? V minus Vs is where we are moving where the source is moving away from the observer or towards the observer. The source will be moving. You see, a very simple way to understand it. If you look at this equation that we get, and how we get it, we come to this intermediate steps in a little while. But if V minus Vs, this value will be lower than V. Therefore, this V divided by V minus Vs is going to be greater than 1. If it is greater than 1, then it is going to be greater than F. F dash is going to be greater than F. So F dash is the frequency that the observer is hearing. And then, when will the observer hear a higher frequency? The observer will hear a higher frequency, means more number of waves per second. When it will hear? When the source is approaching the observer. So, source moves towards the observer, it is V minus Vs. Source moves away from the observer, V plus Vs. Now the intermediate steps. Before I go to the intermediate steps, I want to show you. You just look at this one. Source moves away from the observer. The frequency should be less. So V plus Vs, because V plus Vs is in the denominator. So source moves away from the observer, V plus Vs. Source moves towards the observer, V minus Vs. So now what we can do is we can go to the intermediate steps. And in the intermediate steps, we had this one, lambda dash, and V divided by lambda dash is F dash. So V divided by V minus Vs divided by F, because V is equal to lambda F, right? So lambda dash is V minus V naught divided by F. So here you see wavelength has changed. The frequency of the velocity has changed. The wavelength has changed. The frequency of the waves remains constant. Frequency has not changed. Frequency that the observer sees is going to change. So once you understand these things, you can come up with the final equation, which is f dash is equal to f v plus minus v naught, v minus plus v naught. And you can look up into some of the animations that we have created. Beautiful animation. I hope you will like it. And you see here, now everything is constant. So source speed is 0. I want to move the source towards the observer. And what you will see here is that this brightness will increase. That means more waves, higher frequency the observer will hear. Let's see this. You see? The observer hears higher frequency, right? Okay. Now I want to move, let's put it back to 0. Back to 0, difficult. Hold on. Back to 0. Let's move the observer towards the source, or towards the source. The observer moving towards the source means the frequency is going to go up, right? Put it back, and you are getting all these values, right? You are going to get all these values, and now what I want to do is, I want to put the source towards the observer and the observer towards the source. Okay, let me just refresh it. Observer towards the source and the source towards the observer. Look at this, and you can see very clearly the results. Play around with this, have fun, and in the next session we'll look at some of the problems. But hopefully, after going through this, and the links will all be provided, you will find this topic very easy. And please don't forget to subscribe to the channel. Thank you. Have a nice day. Bye.